Okay, today's lesson is about lesson 6.5, how to graph polar equations and determine maximum R values and symmetry. And we're going to use our calculator for these, so we need to make sure we are in polar form. There are three types of symmetry. There's around the polar axis, which is the x-axis, around the y-axis, which is what we call theta, and around the origin, which is the pole. So here's the first one, and I had it up here, and it reflects across the x-axis or the polar axis, and then it reflects across symmetry about the x-axis. If I have it, and I go across what we call the y-axis, it's over when theta equals pi over 2. That's the symmetry of the y-axis. Or if I rotate it around the pole. Okay, now these are the three different types of graphs. And if you'll notice, on the first symmetry we have r theta. If we come down here we have r negative theta. Or because we can also go backwards, we have negative r and we have negative theta plus pi. Now do you have to memorize these? No. If you're looking at this one, you have the point r theta. You can also have, going all the way over here, r, and it is actually, and you have a negative theta minus, or pi minus theta to get over to here. And then if you go backwards, you have the negative r, negative theta. So all those are to the same point. You can also go over to this one where you have the pole r theta, and you can actually add whatever theta is plus pi to get to this other one, r theta plus pi, or you can go backwards and get negative r theta. So those are all of them, three different ways to say the same point. This just summarizes it, and you'll have this sheet, but you can also look at what your graph looks like to determine if it's the x-axis, the y-axis, or the origin. Now, we could test for symmetry. This is one way to do it. Again, we would put in our negatives and see, based on all the rules that we use with identities, if you end up with the exact same thing. If you do, then it's even and it's symmetric about the y-axis. You can also analyze polar graphs. And then what we would do here is determine the maximum R value, which is the point on the curve that's the maximum distance from the pole. You can also analyze the polar graph, which means you find the domain, the range, the continuity, the symmetry, the boundedness, the maximum R value, and the asymptotes. Now you're going to find maximum R values. If I put this in my calculator in polar form, this is what the graph looks like. Kind of looks like a sideways heart. Now, R theta, and we're going to try and find it as an xy. We can use rectangular equations where theta equals x, and we plug it in, and this is what it looks like in function form. When I look at that, my max looks like a 4. Or, since that seems to be a little harder to do, you could say, well, look, here's my actual equation. Cosine theta is going to have a maximum value of 1 or negative 1. So if I put that in here, 2 plus 2 is 4, or 2 minus 2 is 0. And so my maximum value is the 4. Okay, another example, in example 3, finding maximum R values. We're going to identify the points on the graph. Here's my curve between 0 and 2 pi that give the maximum R values. So if you graph it, this is what it looks like. Now remember, you have to be in polar form. And you could trace the points around and it would show you how the curve goes. And there are 4 points on a graph at a maximum distance from the pole, which is the center. Now what I would do, you would trace it and find it's these values, but you could also look at it and go, okay, cosine goes between plus or minus 1. And where does that occur? And you would say, well, it occurs at 0 and it occurs at pi. So we have 0 and we have pi. But guess what? It also occurs at pi over 2 because 2 times pi over 2 is pi. And if I put pi in here, I get 2 pi, which is these two are the same. And if I put 3 pi over 2, I'm going to get 3 pi again. And so between 0 and 2 pi, I have 4 points. 1, 2, 3, 4. All right? Or you can actually look at it and say, I'm going to put this in my calculator. If I do the absolute value, then I'll be able to know the pluses and the minuses and where they occur. Now, rose curves are just, they look like flowers. They have this kind of equation here, or this kind of equation here, whether it's a sine or a cosine. N is an integer, and it is bigger than 1. Your petals are going to have a length of r, kind of like what we saw up there. If it's an odd petal, it has n petals. If it's an even petals, it's 2, or even, n is even, then there's 2 times that. Okay, in example 4, we're going to analyze this rose curve. We graph it and look something like that. Make sure you graph these. You just don't trust my graph, so that you can see what these look like. Notice this is a 4. So 2 times 4 means I'm going to have 8 petals. The maximum R value, right here, sine is going to go between plus or minus 1. 3 times 1 is 3, and that's my maximum R value. I look at it. It is symmetrical about the x, it is symmetrical about the y, and it's symmetrical about the pole. I can rotate around the pole. So it's symmetrical about all 3 of these places. Domain is all reals. Range goes from -3 to 3. It is continuous. It is bounded. And there are no asymptotes. Now, there are general characteristics of rose curves. This is the general form. N has to be an integer greater than 1. Always, no matter what, on the rose curves, you're going to have all reals, and it's going to go between plus or minus a. It's always continuous, and again, it's going to depend on how many, what's the n value. If it's even, it's going to be symmetric around all 3. If this n value is odd, it's symmetric about the x for the cosine. If the n is odd on the sine, it's symmetric about the y. They're always bounded. They do have a maximum R value, which is A, no asymptotes, and again the petals. If it's an odd number, it's n petals. If it's an even number, it's twice as many. All right, there is another kind of curve. They call it a limison. I think it's French. It has this form of an equation. There are 4 different shapes. Some have an inner loop, some look like a heart on the side, some have a little dimple, and some are just continuous. Alright, and the pictures you see are examples of a cosine. Now, if I do the sine, what ends up happening is that these flip and have horizontal orientations. And here's an example of one. Here it is, r equals 3 minus 3 sine theta. You're going to graph it. Looks like this. The domain, again, is all reals. The range goes from 0 to 6. And how do I know that? I take sine theta, that goes between plus or minus 1. I take 3 minus 3 times 1, and 3 minus 3 times a -1. And that's how I get between 0 and 6. Continuous. Symmetric about the y. I can rotate it across the y-axis. Bounded. Maximum R value of 6. No asymptotes. Here's another limison curve. This one is a cosine. Notice it looks sideways. Has an inner loop. The domain is all the reals. Now, how do I know my range? I take cosine theta, goes between plus or minus 1. Now I'm going to take 2 plus 3 and 2 minus 3. And that's how you get this range. Continuous. No, you can draw this without lifting your pencil. Symmetric about the x-axis. It is bounded. It has a maximum R value of 5, and there are no asymptotes. Alright, here is another example, or the general information about a limison curve. R equals A plus or minus B sine theta, or A plus or minus B cosine theta. The A's and the B's are always positive. It's all reals. Your range, it's going to vary. Don't memorize this. This chart will be given to you. Here's your symmetry. If it is a sine, it's symmetrical about the y. If it is a cosine, it's symmetric about the x. It is bounded. There are maximum R values, no asymptotes. Now there are other types of curves. there is the spiral of Archimedes. You will often see this in like the snail's shell. And then, I don't know what you call these, but I think they're pronounced lemniscate or lemniscate curves. And it looks like it's got squares in it. Okay? So here's the graph of the spiral of Archimedes. It's just r equals theta. It has all reals for your domain, all reals for your range. This keeps going around and around and around. It is continuous. It is symmetric about the y-axis, and it is unbounded, meaning that it goes on forever. There are no maximum values and no asymptotes. All right, the last one we've got here is example 8. We're going to graph this one. It's r squared equals, and it looks like a figure 8, only because we're going between 0 and 2 pi. Now, the domain, how did I get these weird numbers? I'll go through it. The range is -2 to 2. And the reason being is if I go r squared equals 4 cosine 2 theta. This here goes between plus or minus 1 times 4. So r squared is going to be 4, and r is going to be plus or minus 2. We don't use the negative one because the negative one, you can't take a square root of a negative number. So our range goes between -2 and 2. It is continuous. It does have symmetry about the x and y origin. It's bounded, maximum value of 2, and no asymptotes. Now, where do we find these values? Well, we got to solve for r. So we take the square root of this. The square root of 4 is 2, and the square root of cosine 2 theta. Well, since we're looking at the maximum values that we're going to have for our theta, this has to go at 1, which means 2 theta is 0 and 2 pi. Divide by 2, so I get 0 and pi. So that's where my maximum occurs. Now, not every value am I allowed to use, because wherever cosine is negative, I can't take the square root of a negative number. So anywhere where it's negative, let's say for example, here's my cosine. It's negative from here to here, which is in a regular cosine, it happens at pi over 2 and at 3 pi over 2. However, this is 2 theta. So if that's the case, I need to now divide everything by 2, which means pi over 4, which means 5 pi over 4, which means 7 pi over 4, which now means 8 pi over 4. And that's how they got those numbers.